Hi, today we're going to answer the question, does an x86 CPU reorder instructions? And to delve more into that question, we're also going to answer the questions on if it does it affect single-threaded programs? How does it affect multi-threaded programs? Are memory barriers necessary for multi-threading? When should memory barriers be used? What do these words mean if you don't already know? And why is instruction reordering an issue? So the history of x86 briefly. It first came out with its 16-bit version developed by Intel in 1978. The architecture has been very commonly used since and has been developed on by other companies, including AMD. Today, most PCs run the x86 64 version, which is the 64-bit architecture we know today. The biggest competitor to 8664 is the ARM architecture, which is most commonly used in phones and Apple devices. So what is x86 64? Well, it's a CPU architecture which must take a specific input to execute tasks in the system. So essentially you have a CPU right down here, and it has to take in the correct input. So there's abstraction between the programmer written code and the CPU and how it eventually operates. And at multiple points along the way, these instructions get translated into something that is more computer friendly. Since the x86 64 has compiles differently than other architectures like ARM, it runs into its own unique challenges along the way. It also has multiple levels of reordering, as we talked about. The first translation is from user code into assembly language. In this case, it's the x86 64 assembly language. The second is from the translation between the assembly language and the machine code. And the third translation happens during runtime when the CPU needs to reorder in the middle of a call. For example, if something is not found in the cache, it'll first search the cache and then it'll go to a much slower memory retrieval like the hard disk drive. And in that case, it will continue to run instructions while it's waiting for that to come. So it doesn't necessarily always run instructions in the same order with cases like that.
Why does x86 reorder instructions? Just as we can't really understand machine code, the computer processor can't really understand our language. That's where assembly language comes into play. x86 reorder acts as a translator, which takes the assembly provided and converts them to machine code to be executed. x86 reorders the memory interactions of machine instructions according to certain rules, um, as long as it never changes the execution of a single threaded program. x86 has the ability to change the order of low-level operations according to its needs to maximize performance. Each processor is allowed to delay the effect of a store past any load from a different location. As a result, it might end up as though the instructions had executed exchangeable order. How does x86 reorder instructions? Basically, x86 will reorder any stream of loads and stores with respect to each other. If a load or store is ready to execute, the CPU will usually attempt it, despite the existence of earlier uncompleted load and store operations. A program is loaded into the main memory in order to be executed. The CPU runs the instructions stored there, along with reading and writing when necessary. When the processor needs to read from or write to main memory, it first checks whether a copy of that data is available in its own cache. If so, the processor reads from or writes to the cache directly instead of waiting for the slower main memory response. An example of reorder, just imagine running a search on your computer. Basically, your CPU will run the command and will also check the cache for a potentially quicker result, switching to the other command, finding the target first. Why or when is reordering an issue? Since reordering has rules to follow, most memory orderings are not allowed. x86 works to track exactly the original order of loads and stores, and makes sure no memory reorderings that breaks the rules are ever visible. The CPU's rules for memory reordering are only suited for linear non-concurrent programs. The programmer must take more care and writing a multi-threaded program so the CPU knows when to reorder.
Big concept to help us understand why these reorderings happen is multi-threading. Now with multi-threading, there's two big keywords to understand, and the first is process, which is basically the overall program being executed. An example of a process could be an individual Python script that you run, and larger programs like applications have many processes within them. The next word is thread, and a thread is a small process within a process. So these are the even smaller individual things being run within a Python script, for example, say like a function or a file input. So multi-threading more in depth, basically it's a way for computers to handle more than one thing at a time. A lot of programs these days have hundreds of thousands, if not millions of lines of code. And if they were to synchronously execute that code or run it with one thread, it would be very, very slow and would not accomplish anything. With multi-threading though, the CPU can hand out the execution of these instructions to many processes at one time. And this is what's known as happening concurrently. Usually, this process of multi-threading is handled solely by the CPU, but it can also be controlled to some degree by the OS via the programmer. Here's a diagram that kind of illustrates how multi-threading can work, and it's similar to one that we've seen in a lot of our classes lectures. On the left-hand side, thread 1 will run for a little bit, and then a context switch occurs, and thread 2 will get some execution time, and another switch happens, and the CPU will go back to thread 1. And these context switches and the executions of each thread happen so quickly that it seems to be happening simultaneously to the user, but in reality, it's not. And multi-threading in the context of the x86 processor pretty much does the same thing. This processor will split up the instructions and delegate them to different so-called control units. And these control units in part run in parallel. This makes them very capable of creating out of order instructions because the overall thread or process is being split up into multiple control units. Now, a truly simultaneous processor, these have only been implemented in more recent Intel and AMD architectures, typically with 2 threads per core and sometimes even 4.
Here is an example of some multi-threaded code. And in this example, it's essentially just creating a bunch of threads, having them do something, and just returning when it starts and when it finishes. This code was compiled 2 different ways, one way with optimizations and one way without. Typically in a program that does not multi-thread, then the output would be the same no matter the optimizations. But because the compiler compiled it a different way each time, and it doesn't have respect to the multi-threading when it compiles, each output is completely different because it changes the way the loops run, and as a result, it changes the output. So you can definitely get different results between multi-threaded and non-multi-threaded programs, and more care has to be taken to avoid issues like this.
So we've seen that reordering is a pretty big issue, and the main tactic that companies like Intel and AMD use to fight this are called memory barriers. Now, memory barrier is basically a component of the CPU that pretty much has it check itself, and it ensures that instructions before the barrier are finished performing until it moves on to complete the instructions after the memory barrier. Now, these barriers are incredibly important because they help modern CPUs employ these performance optimizations while at the same time protecting them from the unpredictable behaviors that can happen from the reordering. This keeps the CPU running smoothly and happens at the low level part of the code and just makes everything run smoothly. Now, memory barriers inside of the x86 architecture are pretty much the same thing. This architecture does require the use of memory barriers, and this is because they are the foundation. The x86 is the foundation of our modern microprocessors. The x86 does come prepackaged with a memory barrier format, and this means that it's very difficult to find custom or customized memory barriers created by programmers out there. An example of a prepackaged memory barrier is called mFence, and that comes inside every x86 processor. Now, many of these reorderings are not allowed within the x86 architecture because they break the rules. So these memory barriers aren't always necessary, but they do, when they are used, they are very important. And as a whole, our group decided to take our presentation and pretty much donate it back to the overall computer science community. So we've posted a link to this presentation as well as a video format of the presentation on the original StackOverflow thread. And we've also uploaded this video presentation to YouTube for future classes and just everyone in the computer science community to gather from. And these are a small list of our resources that we used. Thank you guys so much for watching. This has been How and Why Does an x86 Processor Reorder Instructions. Thank you.